Transportation routes form an arterial network that affects a country's economic development. The more efficient they are, the better the country can run. Over the past 20 years, Malaysia has begun to rebuild their old colonial single-track railway into a double track to increase line capacity and replace old diesel-powered trains with faster electric train sets which emit 20 to 30% less carbon dioxide. This is the story of the Ipoh Padang Besar Electrified Double Track Project, or EDTP for short, which was awarded to MMC Gamuda to design and build at the cost of 12.5 billion ringgit. Spanning 329 kilometers across the four northern states of Perak, Penang, Kedah and Perlis, the EDTP had to replace the old colonial single track with a double track, one for each direction of travel. The work package included construction of 3 depots, 15 stations, 8 halts, 2 tunnels, bridges including a swing bridge, a control center, power supply buildings, track works, overhead line electrification, and signaling and communication systems. By increasing the capacity and frequency of rail services, businesses and people alike have the choice of a more reliable, cheaper and comfortable mode of transport, which would lead to less congestion on our nation's highways. The new infrastructure would allow an electric train to travel at speeds of up to 160 km per hour, reducing travel time. For example, the previous 9-hour journey from KL to Butterworth could be shortened to just 3.5 hours. Trains are also more efficient by consuming 80% less fuel than trucks, making rail transport 6 times more efficient than road. For passengers, going by rail is 20 times more efficient due to the high volume of seats available in each carriage. Improved freight or logistics facilities also allow the transportation of industrial and agricultural commodities like cement, rice, sugar and rubber products throughout Malaysia and our neighboring countries. Benefits don't stop with trade. Socio-economic development in rural and suburban areas in the 4 states will also be boosted with employment and tourism. As an entry point, stations along the route were developed to contain modern facilities for passenger safety and comfort. In state capitals, royal stations were built to reflect the local architecture, culture and tradition. With grand facades, motifs, colors and other design elements, royal stations were built to become iconic landmarks and tourist attractions. Essentially, the EDTP is about building infrastructure to improve connectivity.
It took us 7 years to design and build the electrified double track project. The first major challenge was to build the new double track on an existing live track. Obviously, the space was confined, and the safety of KTMB train operation and our workers were our top priority. Then came the civil engineering works. The railway track has to be founded on stable and solid ground, particularly for high-speed train operation. So we had to conduct extensive geological mapping on the entire alignment.
From Ipoh, the first major hurdle was Bukit Berapit in Padang Rengas. The old single-track line crossed the mountain in a steep gradient, which became increasingly hazardous for heavier trains to negotiate. The alternative and long-term solution would be to create a new rail track by tunneling right through the bottom of the mountain, which would be flat, stable, and only take around 3 minutes to exit. With a distance of 3.3 kilometers, twin-bore tunnels were created, making them one of the longest railway tunnels in Southeast Asia.
Geotechnicians found that Bukit Berapit is mainly fresh granite. To tunnel through this, the drill and blast method was the best solution. However, safety was a primary concern, and before any blasting occurred, we had a very stringent protocols to ensure the safety of our workers and also our nearby communities.
The drill and blast method requires a drilling jumbo to drill a predetermined pattern of holes to a depth of 4 meters before a detonation device and bulk emulsion explosives were carefully inserted by certified short firers. After each hole was compacted and secured tightly, the area was then cleared before the charges were detonated. Carbon monoxide and other dangerous gases had to be cleared using large ventilation fans before debris could be removed, primary supports installed, and shotcreting to secure the tunnel walls. In total, over 2 kilometers of each bore was tunneled using the drill and blast method with 450,000 kilograms of explosives and over 120,000 detonation devices. 2.38 million man-hours were accumulated, and with stringent safety practices, we were able to achieve the entire process without a single major injury or fatality.
There was also a sections of the tunnel which went beneath the North-South Expressway. In fact, there was only a 5 meters depth from the road to the ground of the tunnel. Any mistakes could lead to fatal accidents, so we decided to micro-tunnel this section. Before that began, we had to place monitoring sensor along the expressway to ensure the safety of the road users.
Without explosives, micro-tunneling causes minimum amount of disturbance and little or no disruption to the expressway above. Pipe jacking is performed with a slurry shield machine, and hollow steel pipes are inserted to form a roof pipe umbrella as a pre-support system that limits settlement of the expressway above. The top half of the tunnel is then excavated, stabilized, shotcreted, and secured before the same process is repeated for the bottom half. Upon completion of the tunneling works, 9 cross passageways were created between the twin bores to provide escape routes in the event of emergencies. A sophisticated tunnel monitoring and control system was installed, incorporating CCTV cameras, temperature sensors, emergency lighting and telephones, and ventilation fans throughout, monitored by control centers in KL Central and Bukit Mertajam. The next challenge arose at Bukit Merah Lake. Essentially a 7,000 freshwater lake, it also serves as a reservoir to a water treatment plant, delivering domestic water to 200,000 people and irrigation for 24,000 hectares of agricultural land. A new 3.5 kilometers marine viaduct had to be constructed across the lake, strong enough to support the electrified double-track railway. During construction, the major concern was pollution to the reservoir, and thus a silt curtain anchored tightly to the lakebed was erected to surround the entire site and ensure that all construction debris would not contaminate the water supplied to the treatment plant. As a result, throughout the entire 3-year construction period, the water treatment plant was fully operational without having to close for 1 day due to contamination. From the marine viaduct, extensive geological testing found that the topography consisted mainly of marine clay, which is very soft and highly unstable. The area was also prone to flooding.
Usually, we would try to remove the marine clay and replace it with earth, or put in vertical drains and compress it to remove the moisture. But when the marine clay goes down 50 meters or more, the only solution would be to build a land viaduct to ensure that the track remains flat and well supported.
Spun piles were inserted into the marine clay, deep enough to reach hard rock and then anchored securely. Piers were then erected to support the viaduct. In total, 28.4 kilometers of viaduct was constructed upon 12,000 anchored spun piles, all the way from Alor Pongsu to Bagan Serai, making this structure the longest land viaduct in Southeast Asia. The next challenge came in the form of a swing bridge located at Sungai Prai. The original bridge was designed to swing open for ferries to gain access to a ferry servicing yard. However, with insufficient width to accommodate a dual track and electrification infrastructure, a brand new swing bridge had to be constructed. In outlook, the swing bridge maintained its appearance. However, its system had to be modified significantly. Since the bridge rests on a central pier and rotates on a central pivot, the mechanism itself had to have an independent power supply delivered by submersible cables with backup generators in the event of power failure. Controlled by a tower specially constructed to monitor bridge operations around the clock, the bridge can only open to allow shipping to pass through upon specific release instructions from KTMB's centralized control once trains are safely stopped. When the bridge is due to open, the controller pushes a button for the tracks to disengage from the power supply, and an intricate process of unlocking mechanisms follow before the bridge rotates to fully open at 72 degrees. With the electro-hydraulic pivot installed, the rotation only takes 5 minutes to complete. Once the bridge is ready to close, it rotates back to its original position, reconnects with the main track and overhead catenary systems, and continues to safely allow trains to pass through. To date, this is the only double-track electrified swing bridge with a horizontal rotation operating in Southeast Asia. To deliver the project in the 71 months construction phase, installation of the 14,000 concrete spun masts required to support 1,500 kilometers of overhead electrified power lines was undertaken in parallel with civil earthworks and track installation. To electrify the line, a complex system was designed that ensures sufficient power reaches the train via a continuous overhead catenary system. Every 20 kilometers along the entire track, traction power feeder and switching stations were built, incorporating transformers to step-down regulated 132,000 volts supplied from the national grid to the 25,000 volts alternating current needed for the electrified trains. Systems planning involved controlling and monitoring train movement along every inch of the track. So extensive and detailed planning was put in place. 850 line-side color light signals, 440-point machines to switch trains between tracks, train detection monitors, and automatic train protection systems are crucial to the day-to-day operations and to ensure the safety of passengers.
We had to design two types of signaling, a temporary system which served the temporary tracks required for stage construction of civil works, and also the permanent one. Both had to be installed to exacting safety standards so that even during construction, rail services could run uninterrupted and safely.
Railway operations are also highly dependent on communication infrastructure that carries operational data and voice communication. Ruggedized fiber optic cables connected underground via ductings were laid beside the EDTP. These cables are steel wire armored and ideal for harsh environments. Used to support signaling, ticketing, station-to-station communications, security monitoring, provision of information to passengers via passenger information display, and many other functions, these cables form the arteries of the EDTP's operational network communications. In total, over 3,000 kilometers of cabling was installed. Upon completion, the digital transmission system, forming the communications backbone stretching from KL to Padang Besar, could be brought to life, and integrated testing with KTMB operations was able to commence. This was completed throughout the entire project area within a period of just 18 months. An integral part of the project is the communications and signaling infrastructure, as these are vital systems that control safe operation of trains. It was also imperative that they were able to integrate with KTMB's Centralized Train Control (CTC) located in KL, as well as a second CTC in Bukit Mertajam that was constructed as a backup in the event that there was a communications breakdown with KL Central. The project was broken up into 8 different packages, involving multi-layer construction where works would begin bottom up. Train laying could only come after all the major infrastructure was in place.
We had to create up to 100 kilometers of temporary tracking in order to dismantle the old and rebuild the new, a process called staging. Once the new tracks were laid, KTMB's existing service continued to use them. This way, none of the usual operations were disrupted.
The EDTP project also contained elements of conservation. In Alusta, the old railway station had a clock tower which served the community as an iconic landmark for 98 years. Very much a part of the local heritage, this station was restored to its former glory. This included the restoration of the clock, which required sourcing for original parts from India. Our journey comes to an end at the last stop of the EDTP line, the Padang Besar station, which includes customs, a large state-of-the-art service and maintenance depot, and a container storage terminal. At the border with Thailand, the track then merged with Thai Railways to continue its journey.
The construction of the electrified double-track project took off in January 2008, with a workforce comprising of 95% local talent. The entire 329 km of the new double track was successfully commissioned and handed over to KTMB in November 2014. This is the story of innovation and determination in civil engineering. There were challenging moments, but as the electric train service begins to operate, we knew it was worth it.